Hi guys, good morning to all. So I am Dr. MUTHUKUMAR. I welcome you all to this online session on force analysis on mechanisms. Uh, there are two types of force analysis. One is static force analysis and dynamic force analysis. So before going to see this, first we must know what is meant by force. Force is a pull or push which acts on the body, change or tends to change the state of rest or uniform motion of the body. So there is an equation for this force is F is equal to m into A. Actually, this was derived from the Newton's second law. So according to Newton's second law, uh, force is directly proportional to the acceleration, where m is the mass. Okay, so unit is Newton. The unit of force is Newton. So next one is applied force and constrained force. The external force is acting on the system of body from outside are called applied forces. The forces existing internally within the body are called constrained forces or internal forces. So it means simply the external forces are acting on the body are called applied forces. The internal forces acting on the body are called uh, constrained forces. So next one, inertia and inertia force. The inertia means the resistance offered by the body to any change of its state, either it may be in rest or in uniform motion, is known as inertia. Actually, it is a property due to which the body is in its own state. Okay, inertia force is an imaginary force which, when acts upon a rigid body, brings it to an equilibrium position. So, according to D'Alembert's principle, the inertia force and accelerating force are equal. Inertia force is equal to minus accelerating force is equal to minus m into a. Next one is free body diagram. The free body diagram is a sketch or drawing of the body isolated from the rest of the machine and its surroundings. Actually, in force analysis, we are drawing the free body diagram of the links of the mechanisms, because these are easy to convert them their analysis. So it means the body is free from the other systems. Only the forces and torque are only represented on the system. So that is the free body diagram. So next one, we must know the difference between the static force analysis and dynamic force analysis. If the inertia effect due to the mass of the component is not considered, it is called as static force analysis. It means here we are not considering the inertia effect. So we should not consider confuse it with the static and dynamic conditions. So static means the condition of rest. Dynamic means it is a motion. So that is not influenced here. Here it is the based on the inertia we are dividing. So if inertia effect of the component are considered, it is called static force analysis. Is not considered, it is a static force analysis. If the inertia effect is considered, it is called as dynamic force analysis. So next one is equilibrium condition. So what is my equilibrium? So equilibrium means the forces are in complete balanced condition is called equilibrium. It doesn't mean it is a zero force. So net force, the here the equilibrium means the net force is equal to zero. That means they are balanced properly. So there are various cases in this. First one, we will see the two force member. Two force member means a body or member subjected to two forces. So in this diagram, there are two forces, Fa and Fb are acting at points A and B. Okay, these two forces. So Fa is not equal to Fb means, and these are acting at different positions means, they in this case the body will not be in equilibrium. So when it will be in equilibrium means the condition is that two forces, you can see this second diagram here, these two forces should be equal and opposite. That is a first condition. So Fa should be equal and opposite. So Fa is equal to Fb and they should be in the same line and opposite directions. These are the conditions for the balancing of the two force member. Next one, suppose if the body is subjected to three forces, it is called as three force member. See, in this case, refer this diagram. Here, three forces are acting: Fa, Fb, and Fc. And these all are acting at different points of the body. Here, this body will not be in equilibrium. So, the condition for equilibrium is the resultant force is equal to 0. How to find the resultant of three forces when it is acting on the body means, here we can use the polygon law or triangle law. Here, if the polygon is a closed one, then it is a resultant force is 0. Suppose if it is not closed, then we can say that there is some unbalanced force in this. Okay, and then this is the first condition: the resultant force of 3 should be 0, and the line of action of the forces should intersect at a point. It means the concurrent forces. Concurrent means all the forces must meet at one point. So according to this, see this second diagram, these three forces must meet at Fa, Fb, and Fc should meet at a point, some point. So this is the second condition. And if you draw the force polygon, they should form a closed polygon. So that is the condition for three force member in equilibrium. The next case, the equilibrium of member subjected to two forces and one torque. So what is mean by torque? So torque is a twisting force. So twisting force, its unit is Newton meter, the force into the perpendicular distance. So torque is the twisting force. So simply we are saying force is it's a linear force. Torque is a twisting force. In this case, in this diagram, this is a body subjected to two forces Fa and Fb, and it is subjected to one torque T. Here torque is acting in the clockwise direction, and these two forces acting on this body, that is Fa and Fb, are acting at some distance of h. So these two forces will form a couple. So couple is equal to force into perpendicular distance, either Fa or Fb into perpendicular distance h. So that is forming a couple. So according to this member, which is subjected to two forces and a torque, the equilibrium conditions are: the forces are equal in magnitude, parallel in direction, but opposite in sense. That is the first condition. And the second condition is the forces form a couple which is equal and opposite to the applied torque. See, in this case, these two forces is forming is acting at some distance. This is one force, this is another force. So these two will make the body to rotate in clockwise direction. See, it will rotate it in clockwise direction, sorry, anti-clockwise direction, whereas the torque applied is in the clockwise direction. So the couple is acting in anti-clockwise direction, the applied torque is acting in clockwise direction. So these two are equal and opposite, so then the body will be in equilibrium. So this is a condition. Suppose in this case, if we are applying torque in the same anti-clockwise direction, we cannot balance the, or we cannot bring it to the equilibrium condition. So we have to change the direction of this torque in this case. So the equation is torque T is equal to, here torque T is equal to couple C, where couple is equal to force into perpendicular distance, that is Fa into H or Fb into H. Because these two forces are equal, must be equal, so we can take any one force and perpendicular distance H is taken. So we can bring it to the equilibrium condition. So now we will see the problem. It is a mechanism. So we know mechanism, slider crank mechanism. You know where it is used. So it is mostly used in our IC engines and compressors. We are using this slider crank mechanism. It's used in many machineries. So mainly it is major application is we are using it in the IC engines and the compressors. So the slider crank mechanism, what is my crank? We must know what is meant by crank, what is my connecting rod, what is meant by slider before going into this. The crank is the link which is making a complete rotation is called crank, and the slider is a link which is making a pure linear motion. So what is connecting rod? The connecting rod is a link that is connecting slider and the crank. Okay, so in this slider crank mechanism there are totally four links. First one is a fixed link, and second one is the crank, third one is the connecting rod, and fourth one is the slider. So in this case, in this problem, in a slider crank mechanism as shown, the value of force applied on slider 4 is 3000 Newton. So here the 3000 Newton is applied here on the slider. At point C, we are applying a force of 3000 Newton. The question is determine the forces acting on various links and also calculate the driving torque T. Here the torque T is applied on the crank in clockwise direction. The torque is applied. The link dimensions are given as link AB, that is crank length is 100 mm, and BC is the connecting rod, its length is 300 mm, and the angle BAC is, that is a crank angle with the line of stroke is 60 degree. So this is a given problem. So for this problem we have to draw the we have to find out the forces and torque for equilibrium condition. So this is a problem we have to solve. This is a static force problem. We will see how to solve this. Before solving this, first we got to draw the space diagram. The space diagram is nothing but we are drawing the diagram to some scale. Space diagram or configuration diagram, both are same. So here we cannot draw the mechanism to original scale. So we are using the scale. So we are reducing the scale. So we can suitably select the scale for our diagram depending upon the dimensions, both the major length and minor length. Based on that only we got to select a scale. Here minimum length is 100 mm and maximum length is 300 mm of the link lengths. So we are selecting 40 mm as the 1 centimeter. So we can draw the diagram suitably, and it is visible. So first, from which point we got to start this space diagram? So that is a question. So here we should start from the point A. So first of all, we got to mark the point A. It's a fixed one. So that is a link 1. And we got to, this is a first point. We got to start from here. First, then we got to draw the line of stroke. This line of stroke is drawn. And with reference to this, using pro circle, we are marking 60 degree angle and we are drawing this crank. So what is the length of the crank? So its original length is 100 mm, but our scale value is 1 centimeter is equal to 40 mm. So the drawing length of this crank is 100 divided by 40, that is equal to 2.5 centimeter. So at 60 degree angle with the line of stroke, we are drawing this line to represent the crank. So this is link 2. So this is link 2. Next, you take a compass and you take this point B as the center, and the connecting rod length is 300 mm. So 300 mm is the original length, but our scale is 40 mm is equal to 1 centimeter. So 300 divided by 40. So that much of centimeter is to be taken in the compass, and take B as center and draw an arc on this point on the line of stroke. So from there we are marking the arc, that is point C, which is the center of the slider, and you take that point as center and you draw the slider also. So slider is drawn here, and we are marking the applied force, externally applied force. F is equal to 3000 Newton on it. Okay, and then we are marking all other dimensions, and we are marking the notations. So this is a point A, point B, point C, and then the link numbers are the fixed links. There may be n number of fixed links. Here at 2 points it is fixed. One is here and another one is here. Here this is the cylinder inside our guide, within which the slider is making a motion. So here link 1, the fixed links are all are, even there may be n number of fixed links, we are taking it as a single link. And then the crank is link 2 and connecting rod is link 3 and the slider is link 4. So after first we have to complete the space diagram properly to some scale, and we got to mark all the dimensions, all the notations and names of the points. So this is the first step. So next one is we have to draw the free body diagram. See, in drawing free body diagram here, we have totally 4 links. In 4 links, one is fixed. So remaining 3 are in motion. That is a crank, cutting rod, and this slider. So these 3 are in motion. So we have to draw the free body diagram of these 3. So first we will draw the which one is to be drawn first, either crank, cutting rod, or slider. So if you take this crank, here it is subjected to 2 forces. From link 1, one force is acting on 2, and link 3, one force is acting on the link 2, and another one torque is applied T. So it is subjected to 2 forces and 1 torque. Next, if you come to this cutting rod, it is subjected to 2 forces. One is link from link 2, one force is acting on link 3, and from link 4, one force is acting on the link 3. So it is subjected to 2 forces. Next, if you come to this slider, it is connected with link 3 and link 1. So one force will act from this link 1, that is F14, and one force will act from the link 3 on link 4, that is F34, and externally we are applying one force, that is 3000 Newton. So it is subjected to 3 forces. So if you take crank is subjected to 2 force and 1 torque, the cutting rod is subjected to 2 forces only, and the slider is subjected to 3 forces. So out of these 3, the simple diagram or system or link is, there is a link 3, there is a cutting rod, it is only subjected to simply 2 forces. So first we will take that link and we will draw the free body diagram of that. So this is a free body diagram of link 3. Say in this, just we have to use the mini diopter or roller scale, and we have to exactly copy the same link at the same angle and the same length, and we have to copy here. So this is the link free body diagram of link 3. Here we are removing all other adjacent links, only the link 3 is represented, and the forces and torque acting on this are represented. So according to this, one force will act from link 2, so that is F23, and one force will act from link 4, that is F43. Initially we don't know its direction. We have seen already that when a body is subjected to 2 forces, the condition is, equilibrium condition is, that 2 forces must be equal and opposite. So according to that, if we take that F23 must be equal and opposite to the F43. So again we are drawing this vector parallel and opposite to each other, that is F23. So why we are representing F23 means the force is acting from link 2 on link 3, so it is represented as F23. Here also from link 4 it is acting on link 3, so it is taken as F43. So F subscript 43. Okay, from 2 you take like this, from 2, from link 4 on link 3, so we should represent like this. And then so we know that for equilibrium these 2 forces must be equal and opposite. So F23, actually it should be as subscript F23 is equal to F43. These 2 are equal and opposite. Next, with this you link 3 is over. Next you come to this link 4. So in this link 4 we are drawing the free body diagram of link 4. So here it is subjected to 3 forces. One is F34, from link 3 connecting rod, force is acting on link 4, so we are representing it as F34. this F34 and F43 are equal and opposite. Okay. Next, from link 1, the force is acting on link 4, that is F14. From 1 on link 4, so F14. So next one is the external force F is equal to 3000 Newton is applied. Just a minute. So this is external force acting on the system. So here this body is subject to three forces, F34, F14 and F. We already seen when it is subject to three forces, the two conditions are to be satisfied. First condition, the polygon, force polygon must be a closed one, and second condition is there should be a concurrent forces. We know that here the forces all are meeting at this point, so automatically this is forming the second satisfying the second condition, concurrent forces. So second condition is satisfied. Now we have to check whether it is following the first condition or not. For that we are drawing the free body diagram, sorry, force polygon diagram. So here out of three forces, for this externally applied forces only we know the magnitude and direction. For other two forces we know only the direction. So first we are taking this force F, and this value is 3000 Newton. So we have to draw the force polygon. For that we are taking a scale of 1 centimeter is equal to 500 Newton, and we are first starting from this point. Okay, first we are drawing this horizontal line. Actually its value is 3000 Newton, but scale value is 500 Newton. So 3000 divided by 500, 6 centimeter. For 6 centimeter we are drawing the line, and then this horizontal line in the same direction. For other two forces F14 and F34 we don't know the magnitude, but the directions are known. So simply we are drawing the line parallel to that forces. So this F14 is drawn from this point parallel to this. So we are simply drawing this line and we are extending it on both sides. And then from the starting point we are drawing this third force, that is F34. We are drawing from here, we are just extending, we are extending it on both sides. So these two forces will meet at one point. Okay, now we are completing this polygon by connecting this, and we are omitting all others. So now we will get a complete polygon. So here this is F14 and this is F34. Now we can from this we can calculate this values of F14 and F34, that is given in the next slide. So this one here we have to measure this length of this F14 in centimeter. Actually this value is F14 is equal to length of vector F14 in centimeter into scale factor. Its value is 2.1 centimeter. The scale factor we have taken is 500. So 2.1 into 500, 1050 Newton. And next you measure this length of F34 vector in centimeter. Actually this value is 6.3 centimeter, and multiply by the scale factor we will get 3150 Newton. So we are calculating from this force polygon, we are calculating this F14 and F34. So we know that F34 is equal to F43 is equal to F23 is equal to F32 is equal to 3150, because the equal and opposite forces are same. So after calculating F34 we are easily finding the other forces, that is F43 is equal to F23, F23 is equal to F32. So all are same, so their values are same, 3150 Newton. So next, already we have completed the free body diagram of link 3, that is connecting rod and slider. Finally we come to the crank is link 2. So here we are, this link is subjected to two forces, that is F32. From link 3 it is acting on link 2, so it is called as F32. And then from fixed link one force is acting, Actually, we don't know its direction initially. Only the direction of F32 is known, but F12 is unknown. Okay, and just simply initially we have to mark like this and represent this torque. Okay, so this link 2 is subject to F32 and F12 and a torque of T. So according to equilibrium conditions, when a body is subjected to two forces and one a torque, the equilibrium condition is that two forces must be, that is F32 and F12 must be equal and opposite. So after applying that condition only, we are drawing this force F12 just opposite to this link F32. Equal and opposite direction we are marking at this point. So now only we are finding the direction of F12. After applying the equilibrium conditions, we are finding the direction of F12. Now we know that condition. The torque is acting in the clockwise direction. So it will try to rotate the body in clockwise direction. Whereas the couple is formed by the two forces F32 and F12. Here the shortest distance between these two is h, so that is to be taken or calculated from this diagram. Okay, and that value is 0.1 meter. Okay, so F32 and F12 are already we know F32 is equal to 3150 Newton. So by multiplying this we will get 315 Newton meter. So that is the couple. That couple must be equal to this torque. So torque is also 315 Newton meter. So the final solution is so when a body is or when a mechanism is subjected to this forces, when we are applying 315 Newton meter of torque, it's calculated from here. So 315. So 315 Newton meter is calculated. So in this case, when we are applying a torque of 315 Newton meter of torque in clockwise direction, this entire mechanism will be in equilibrium condition. So this is a way of calculating this. In the same way, we have seen for one more problem. So this is a 4-bar mechanism. 4-bar mechanism is having 4 links. Here also, one is fixed link, another one is crank, and right side this is a rocker or lever. So this is a crank, link 2 is the crank, and link 4 is the rocker or lever, and this link is connecting crank and rocker. So this is called as connecting rod. So in this problem also the dimensions of the links are given and the angle of inclination of the crank is given. So here additionally one force is acting on the rocker or lever, that is external force, that is equal to F is equal to 2000 Newton. It is acting at 45-degree angle. So here again we have to draw the space diagram to some scale. So after drawing this space diagram, here also the connecting rod is only subjected to two forces. Here we are drawing the free body diagram of connecting rod. So because it is subject to only two forces, so we are drawing the free body diagram of connecting rod. After that, we are drawing the free body diagram of rocker or lever. Here it is subject to three forces. So as usual, we are drawing the force polygon. And then after completing that, we are coming to this crank. Here this link is connected as subjected to two forces and one torque. So similar to the previous case, we are solving and we are finding. Here additionally one more difference is here we have to find out the direction of F14. So because here F14 direction is unknown, so for this we are using this technique. First initially drawing the free body diagram of this link, that is a rocker, and then we are representing this link force external force F, and we are marking the F34. We know its direction because it is parallel and opposite to the connecting rod, and this direction is unknown, initially unknown. So we are extending this force and this force. So according to the equilibrium condition of three force member, the third force should also pass through this point. So we know the point of application of this force. So we are connecting these 2 points. We are connecting these 2 points, and we are finding the direction of F14. So this is an additional case compared to the previous case of Slider-Kang mechanism. So this one additionally we got to find out the direction of F14. After finding this F14, we can draw the force polygon to some scale. Here only one known value is 2000 Newton. That is applied force. We are taking some scale either 1 centimeter is 400 Newton or 500 Newton as 1 centimeter. We can take, and we are drawing the other two forces parallel to that direction. So from the intersection of them, the two forces, we are finding their values. So we are measuring the length in centimeter, and then we are calculating the dimension of them. Finally, we are drawing the free body diagram of the crank. Here also, that it is subject to two forces on one torque. We know the calculating forces and perpendicular distance. So by multiplying this, we can get the couple. So from the couple and the torque are equal and opposite. So from this, we are calculating the torque. So this is a way. Here we must use the proper drawing instruments, and we should take almost care while drawing the diagrams. So then only we can get the exact solutions. Even if you are making a slight changes in the angle, then you will get the different answers. So we have to draw it very carefully while drawing this diagrams. Thank you for watching.